everybody. Hello. My name's Anjana, lawyer. No, my name's Anjana Vakil. I am so happy to be back in Cluj. I have had the amazing honor of being a co-MC and speaker at JSHeroes many times in the past, and it is always one of my favorite times of the year where I get to come and hang out with you beautiful people. So thank you for being here with us. Since Bogdan already covered the functional programming, I'm not talking about functional programming. Instead, I'm going to talk to you about making waves with the web. Before we dive into making waves with the WebAudio API, it's post-lunch gloom moment. We're all in food coma. So I'm going to be the annoying person who has the microphone and gets to do whatever they want. And I'm going to ask you all to join me in making a wave from this side of the room to this side. That means standing up and putting your arms up and yelling, woo, as much as you can. OK, ready? Starting here. Go! Yay! Thank you, everybody. All right. Great job. Great job. Now, if you thought that was loud, get ready, because this is a presentation about audio synthesis and data sonification, and there's going to be some noises that my computer and the very awesome speakers are going to make. And so if you are sensitive to sound or don't want to hear arguably ugly noises blasted at your eardrums, you're free to leave. I won't hate you, don't worry. All right, so I want to talk to you about audio synthesis and data sonification using the WebAudio API. Data sonification. Has anyone heard of it? I see a couple of hands. Have you heard of data visualization? Almost everyone. Yeah, but why should visuals get all the fun? We have other senses. We have other ways of understanding the world around us. And so data sonification is analogous to data visualization, where we take attributes of our data set and we map them to different properties of pixels on a screen, like the height of a bar or the color. In data sonification, we do the same thing, but in the world of audio. So that's what we're going to be looking at. And there are a lot of amazing examples of data sonification projects out there, but there's one that I've just been such a big fan of probably for the last 10 years. It's been my work soundtrack. And this is a project, an artistic project called Weather for the Blind. You can check it out at weatherfortheblind.org. Before I say more about it, let's have a listen. Trippy, right? Let it wash over you. Okay, so what we are hearing right now is New Orleans, Louisiana. This is essentially, you can see sort of in the background here, an analog synthesizer instrument, which is essentially a box with a bunch of circuits inside of it and a bunch of twiddly knobs and dials and things. That was created by an artist named Quintron. The instrument's called the Weather Warlock, and there's also a band that sort of performs with this. And the Weather Warlock is this analog synthesizer instrument. You can hear there's always a noise coming out of it. So unlike, if you're like me, when you hear the word synthesizer, you picture a keyboard, where when you hit a key, a noise comes out. When you stop hitting a key, eventually a noise stops happening. This is called a drone synthesizer, where it's always making a noise. It's got that droning, there's constant sound coming out of it. Now, although this was built by a human, this instrument is not being played by a human. And no, it's not being played by AI either. It's being played by the weather. That's right. If you can see way in the background over here, there's a little weather station with some sensors for things like wind speed, temperature, rainfall, et cetera, that is hooked up to essentially the knobs and switches on this instrument, and it is modifying them as the atmospheric conditions change, the atmosphere of the sound changes. So I've always thought this is ideal working music because there's no lyrics, I can't get distracted, it's chill and calming. There's a lot of other examples here of what does it sound like when there's a storm? What does it sound like when the sun rises? So you can check this all out. For now, we're going to tune you down. Okay, thank you. Thank you, Weather Warlock. So I've always thought this would be so cool to learn more about audio synthesis and try to recreate a project like this on the computer. And then luckily, I found myself in the perfect situation for doing that, a little place called the Recurse Center. Has anybody heard of the Recurse Center? A couple of hands. Did you hear about it from me? Probably, yes, because I love talking about the Research Center. It is where I first learned JavaScript, first started learning JavaScript, let's say that, because I haven't learned it, in 2015. And it is a place where you can go and do a writer's retreat, but for writing code instead of writing poetry or novels or what have you. So if it sounds interesting to you to be able to work on whatever your curiosity points you towards in the world of programming, surrounded by a community of like really interesting peers who are really motivated to help each other, check out recurse.com, read all about it. But suffice it to say, it's a place where you get to work on weird projects, whatever you want. And so one of the fun things we do at the Research Center is something called Impossible Stuff Day, where in the morning, everybody shares an idea for an impossible project that sounds impossible to them. They try and build it that day, and then at the end of the day, we share how far we got. And so I was like, perfect, I know something impossible, synthesis. How? I don't know. Draw the owl, right? Just draw it. I have no idea how to synthesize a sound. And how do we go from taking waves, because that's all that sound is, it's waves that have a certain frequency that hit our eardrums and produce magical feelings inside of us. How do we go from that to like an interesting soundscape like this project? And if you're like me, you start researching and you immediately get overwhelmed and want to hide because there's so much jargon. There are so many acronyms. There are so many little words that I thought I knew the meaning of in English that have a totally specific meaning in audio land. And it's all very overwhelming. Now, luckily, I was surrounded by the Research Center comrades that pointed me to some helpful resources, including an amazing course, free video course that's an intro to sound synthesis from an artist named Sarah Bell Reed, who makes really cool synthesized electronic music. And really, she breaks it down in such a helpful way, and that's what I would like to try to pass on today. She has a 3-step breakdown of how we make synthesized music. First, you gotta make some sound. That's gonna be kind of like the raw material that we're gonna work with. Then we're going to shape that sound, just like a sculptor shapes the clay or what have you, to make a unique, kind of hopefully pleasing, maybe pleasing, sound. And then to add some dynamics and to add some different energy and different interest, we're going to move sound. So these are the 3 steps. First, we need to make sound, then we can shape sound, and then we can move sound, and then we will have magically an ambient soundscape that I get to do my work to. Okay, so let's break it down. Now, we don't need to download any special software. Like Sarah Bell Reed uses a system in her course called VCVRAC. It's a desktop software that's very cool, but we don't need it because we have a web browser. And the web browser has WebAudio API. And the WebAudio API is pretty amazing. It's widely available, and you can dive into it for like the rest of your career if you want to, I think. You can read all about it on MDN. We are just gonna scratch the surface of what it can do, but suffice it to say, it makes it possible for us to do whatever we want with sound in the browser. And there is an amazing project for learning the WebAudio API that I just, luckily for me and luckily for all of you, just found out about the other week. It's a project called WebAudio Studio, which essentially gives us a visualization of what the WebAudio API understands in our code and how sound flows through a graph, essentially, of different operations that the WebAudio API is doing. So this is a really amazing tool to play around with the WebAudio API. You can find it at webaudio.studio. It's by a developer named Alex Griss. I'm so grateful that this thing exists. And that is where we are going to go next. So let's hop into our WebAudio Studio. Can we read this in the back? Yes? OK, excellent. So when what we're going to have here is on the left, we're going to have some code in JavaScript, and on the right, we're going to see eventually the audio graph that we get from this code. The first thing we need to work with the WebAudio API is an audio context. And you can think of this very similar to like the Canvas 2D context or something like that. So first thing we need to do is get a new audio context. And there are some gotchas here. We don't want to do that like without the user telling us, yes, I would like some sound coming out of my computer right now. So we have to wait for user interaction and things like that. But suffice it to say, once we've got our audio context, we can start working with it. For brevity, I'm going to rename this CTX. And if we generate the graph here, we see that once we create an audio context, we get something called an audio destination. And this is essentially going to be like my speakers or my headphones or whatever my sound output might be. And so we're gonna be able to work with that later. It's going to be important for us to be able to access it as context.destination. We'll come back to that in a moment. Now, you may have noticed that there is no sound happening. Can you hear anything? I can't hear anything. Can you hear anything? No. We have not made sound yet, so let's get to it. Step 1, make sound. To do that, we're going to use an oscillator. An oscillator is a little thing that oscillates, goes back and forth at a particular frequency, a particular number of times per second. And essentially what that does is it creates a wave. And that is going to be something that our ears and our brain can interpret as sound. So we can do that in our WebAudio API with a method called, on our context object, we can call create oscillator. I love it when things are named clearly, don't you? And when I run that, we'll see that we have, in addition to our destination node, we have an oscillator node. Now, we're going to talk more about what all we're seeing here in a second. But right now, these are not connected in any way. And so what we have is the oscillator node is essentially a sound source. It's something that's going to be creating sound. Then we have the destination is a sound sink. It's something we want to send sound into. And what we need to do is hook them up. We can do that with the connect method on any of these nodes. So I'm going to capture this oscillator node as os. Typing is hard. And then I can call os connect and pass in the node I want to connect it to, in this case the destination. And now they are connected. Yay. But I still don't hear anything. Do you hear anything? I don't hear anything. Do you hear anything? No, I don't hear anything. OK, that's because we haven't actually set the oscillator moving yet. We can do that with oscillator start. Now, let's hope that the volume is reasonable. Let's see what happens now. We made sound! Yay! OK. We're going to pause there for a moment. Before we go any further, I want to talk about another piece of jargon, which is gain. So gain is one of those common little English words that I thought I understood, but no, it has a specific meaning in audio land. Maybe you've seen a gain knob on like your home stereo or like other audio equipment. Essentially, if we have increase in gain, we have an amplification or more loud for the signal. And if we have a lower gain or a negative gain, what we're going to do is attenuate. Instead of amplifying, we're going to attenuate or make more quiet the signal. Don't you wish you had a gain knob for me? Wouldn't that be cool? Yeah, sorry. So we can create a gain node in our WebAudio API. I'll name it gain, because I'm that creative. And luckily, they also were as creative as me, because the method to create a gain is called create gain. Yay! So now, if I create a gain node, we'll see, pause. OK, we'll see that I have a gain node, but it's not connected anywhere. So I can connect it up now. Basically, instead of connecting my oscillator directly to the destination, I'm going to connect it to the gain. And then I'm going to connect the gain to the destination. And now we are going to hear the exact same thing we were hearing before, because the gain by default is 1, which means no change. I can change that by setting the interestingly named gain.gain value. So let's say I turn this down to like 0.3. Now, hopefully, we have something a little bit more reasonable. OK. Now, I'm going to pause the audio there. Now, the reason I wanted to insert some gain here is because I want to show you some uglier noises than that. Now, if we notice, when we hear this sound, we hear basically one note, right? What we're hearing is the frequency 440 hertz, which essentially corresponds to an A note. I want to say A4. The musicians can correct me. So essentially, by default, this is what's called the frequency, which has a value for the oscillator. And right now, it's 440, which we hear as an A note of A4. If I cut that in half, we hear the same note 1 octave lower. And now I'm going to turn this down even more. If I double 440 to 880, we hear the same note 1 octave higher. So there's a relationship between, there's a relationship between the frequency of our oscillator and the sound that we hear. It's not linear. But basically, anytime you double the frequency, you're going up an octave. Anytime you halve the frequency, you're going down an octave. And so different frequencies make different notes. I'll put it back to 220 for all of our eardrums' sake. And we're hearing that one very clear note right now because the type of oscillator here, which we can access with oscillator type, is a sine wave. So this is creating a nice smooth transition between the highest energy and the lowest energy, so sort of +1 and -1. It's smoothly transitioning. And a sine wave is like the purest form of a sound wave. It's a single frequency, essentially. But there are other shapes of wave we could use. For example, here is a triangle wave. Sounds slightly different. This one is called a sawtooth wave. OK, that's why I put the gain in there. Let's go back to our triangle. All right. And what we can see in the amazing Web Audio Studio that I love so much is we can see the actual shape of the wave changing here. And as a shortcut, I can click these little buttons to switch between the different shapes. And I can turn the gain up a little bit so we can hear a little bit more. Different, right? This one is called a square wave. Oh. And then the sawtooth wave is very fuzzy. So these all sound different to you, right? Are you hearing different noises? Excellent. OK, great. Why? Why are we hearing different noises? These are all set to the same frequency. Well, we can check that out using, there's an awesome little analyzer node we can pop in here. This is basically, by default, showing us the amount of energy in the signal over time, which is the same thing as what the oscillator visual is showing us. But with some fancy math called a fast Fourier transform, we can look at the signal over time, and we can break it down into all of the different frequencies that are contained within that signal. I'm going to zoom in here, and we can get a breakdown in the frequency spectrum instead of the time spectrum to show which frequencies are represented in the sound we're hearing. So this is a sine wave. We basically only hear that one note. Turn it up a tiny bit. And you can see this in the frequency breakdown. It's impossible to read the thing here, but trust me, this is at 220 hertz, which is our base frequency or our fundamental frequency. And what this shows us is that essentially there's only one big peak in this signal from the sine wave, and that's why we hear one simple tone. But as soon as we switch to a different wave type, it looks completely different. Because it sounds different, and it looks different, and we can see what's happening here is that in the higher ranges of frequency spectrum, we have more additional content in our wave now. These are called harmonics. These higher frequencies that are included in our signal are essentially kind of multiples or different, a different spectrum of harmonic tones that are based off of our base or our fundamental frequency. And the different shapes contain different spectra of harmonics. So the sine wave has basically none, but the sawtooth has everything all at once, and they're all slightly different. And so this shape, this creates these different feelings of sounds, or different timbres, you might call them. Okay, pause. So what we've got now is some raw material. We have made some sound, and now we can proceed with shaping our sound. Now, we've already modified the shape of the sound a little bit just by switching between these different types of waves, these different shapes. But where things get really interesting is once we start using filters. I told you I wasn't going to talk about functional programming, slightly. No. But just like a filter on a JavaScript array lets us decide, OK, I want these parts, these elements from the array, keep those, and those other elements from the array, filter those out. I don't want those. A filter in the audio space, or an audio filter, essentially is doing this for each different frequency in our frequency spectrum. So the filter is essentially a function that we apply to our incoming signal, and it says, OK, for this given frequency, I want more of it. I want to amplify it. Or for this given frequency, I want to turn that volume knob down. I want to attenuate it. And that, how much signal we are amplifying or attenuating is the frequency response of the filter, and that's kind of what defines the filter function. Now, most filters are kind of oriented around what's called a cutoff frequency. This is essentially a threshold that's sort of like the test function that we pass into a filter on an array that says, OK, if it's higher than this, keep it. If it's lower than that, throw it out. And so different types of filters operate differently around their cutoff frequency. So for example, a low-pass filter says, OK, anything lower than the cutoff frequency, you're good. You get to pass through. Low pass. Anything higher higher than the frequency, than the cutoff frequency, I'm going to attenuate. And the further away a frequency is from the cutoff, the more it's going to get attenuated. So there's a bit of a roll-off in this shape of this filter function. And so let's see how that looks in our studio. I can create a filter. I'm going to call it filter, because again, love naming. With the method on my audio context called create biquad filter. Now, I am not going to speak at all about the math, the very complex and interesting and above my head math that goes into audio filters. You can do an entire career on that, too, if you want. But suffice it to say, there's a couple of quadratic equations doing the heavy lifting here, and that's why it's called a biquad filter. Regardless, we're going to create a biquad filter node, and I'm just going to stop the oscillator for now. We've got a filter node. We need to connect it into things. So instead of connecting the oscillator directly to the gain, I'm going to connect it to the filter. And then I am going to connect the filter to the gain. And now we have them all set up. So let's try starting our oscillator and see if we can hear any difference. So we've still got our triangle oscillator. This is with a low-pass filter, and by default, its frequency, its cutoff frequency is, I think, 350 hertz. Hard to read, just trust me. We can change that with filter frequency value. Let's say I make it higher, like 600. Let's see if you can hear a difference. Maybe if you're very keen, you could have heard a little bit. Let's look at what's going on with an analyzer. Okay, zooming in a little bit. So, I'm going to turn off the filter briefly, another amazing feature of WebAudio Studio. That's our plain old, turn the gain up slightly. That's our plain triangle wave. We're using a triangle wave to give us some of that nice material in the higher harmonics. And if I turn the filter back on, listen for the difference. Can you hear a slight change there? Cool. And if you notice, you can see it as well. What we're seeing is essentially, you can imagine that the shape of this filter here is like overlaid on the incoming signal, and we're dampening the higher frequencies. Now, analogous to a low-pass filter, which this is by default, we have something called a high-pass filter, which I can change the type of the filter with filter.type. If I change this to a high-pass filter, it'll sound different. Let's try low pass again. Pretty different, no? Hear the difference? And so what's happening here is that in a high pass filter, it's the opposite. So where before anything lower than the cutoff frequency was being let through, passed through, anything higher than the cutoff frequency is cut out. In the high pass filter, it's the exact opposite. Anything higher is okay, anything lower is tuned down. And so here we're losing almost all the low end of the spectrum here. So suffice it to say, there's like a ton of different filters, different shapes you can play with here. But we're going to work with a low-pass filter for now. OK, where things start to get really interesting is when we introduce resonance into our filters. So resonance is essentially we're talking about, when we talk about resonating with something, it's like, oh yeah, that really strikes a chord with me, right? And in the sound domain, when we talk about resonance, we're talking about amplifying a particular frequency. And in the context of filters, a resonant filter is one where there is amplification around that cutoff frequency. So you could think of this as almost like we're adding a peak. We're pulling up the frequencies at the cutoff, amplifying them even more before we start the roll-off of attenuating the higher signals. So let's add some resonance to our WebAudio filter. We can do that with a mysterious parameter called Q, whose value has no unit. There is no unit of this. It's just a number. And it just corresponds to more Q, more resonance. That's all. Try reading about it. Explain it to me. I dare you. OK? But yes, ostensibly this stands for filter quality. And by upping the filter Q value, we can add more resonance to the filter. So if I try this with like a value of 5, let's say, hopefully you'll hear something a little bit different than the default value of 1. Let's start with a default value of 1. Now see if you can hear the difference if I turn it up to 5. Anybody sensitive to that? Now let's see if we can turn up to like 15. See if you hear anything. you're starting to hear like a higher note in addition to the main one, in addition to the fundamental. That's because, and we can see it in our frequency breakdown, what we've got, and again, I have this amazing little knob where I can turn down the resonance. If I turn this back down to 1, we'll see the peak of that filter function drops, and so does one of these higher harmonics, one of these peaks that's there in the original signal. When I tune up, you see that peak rising with the higher Q? And what that's doing is amplifying that higher note that you hear in addition now to the lower one. So, now, what happens if we change the cutoff frequency of the filter? Let's see if you can hear it if I turn this up to like 1200. Now we hear a different higher overtone, essentially. And if I were to turn this down to like 400, it's a little bit harder to pick anything out because it's so close to our bass. But essentially, as I change the cutoff frequency, I'm gonna pop an analyzer in here so you can see. As I increase the cutoff frequency, that peak is moving through our higher harmonics, and it's amplifying a different part of the harmonic spectrum. Do you hear that sound changing as I move this manually up and down? Whoa. Yeah, a little bit? I'm seeing some nodding. Okay. So what we've just started doing here, you're welcome, I paused it. What we've just started doing here is moving sound. I was doing it manually, but what we just heard, that's me doing an impression of a filter, sweep. This is called a filter sweep, where we dynamically change the cutoff frequency of the filter. And that adds this interesting motion in the overtones, in the harmonics that we're hearing. And this creates all kinds of different like atmospheric effects. And once you're aware of what a filter sweep is, as I recently became, you will hear them all over the place. Like in things like the Stranger Things theme music or like all kinds of electronic music, filter sweeps are all over the place. So that's what we just did manually by adjusting the knob of the filter's cutoff frequency. Now, what happens if we make that an automatic process? There's a concept, one of the fun acronyms that I had no understanding of 6 months ago, LFO. It stands for Low Frequency Oscillator. Now, this is essentially the same thing as the oscillator that we used to make sound. It's just going to operate at a much, much, much lower frequency. And that's going to allow us to get some interesting dynamic movement happening in our sound graph. So luckily for me, and luckily for you, because I am also running out of time, I'm going to avail myself of, there's a bunch of really awesome example graphs in WebAudio Studio that Alex Griss has like gifted us with here. So you can check out a whole bunch of different things, but I'm going to avail myself of the LFO modulation graph. So let's load that up and take a look at what it's doing. Now, first, I'm just going to turn off the oscillator so that we don't hear anything yet. OK, so now what we've got is a similar graph to what we just had, where we still have our oscillator node piped into a filter with a resonance. It's a low-pass resonant filter. There's a gain node, and then we go to the destination. But the new part is we now have another oscillator node that is created right here. OK, so here we have another create oscillator call, exactly the same as our first oscillator. It also has all the same shapes. In this case, it's a triangle, except its value is like way, 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 way lower. So instead of moving back and forth 220 times a second, this one is moving back and forth once every 2 seconds. Now, we can't hear that if we were to listen to it. It's too low for us to pick up on as humans, as a sound. But we can use it as a dynamically changing value that then we can hook up to other parts of our graph to dynamically change things. So what we're going to first do is scale up the amplitude of this signal with a gain node. So we've got another gain here that's called LFO gain. Set that value to something that's like audible, in this case 600. And so now the LFO by default is going from +1 to -1, +1, -1. We're multiplying that by 600 to get like +600, -600, +600, -600. And what we can then do is once we connect our LFO to the gain, to the new gain, and then connect our LFO gain to the filter's frequency parameter, we now get, essentially, an oscillator. The low-frequency oscillator is modifying or modulating the frequency of the filter's cutoff. And if we pipe in our oscillator to this, you should hopefully be able to hear the movement now. I mean, it's different, it's weird, and I'm not touching anything. This is the computer doing it for us. Okay, pause. So, we've now made sound with an oscillator, shaped sound with a filter, and moved sound with a low-frequency oscillator. And if we take these basic building blocks, and I am out of time, so we're not going to see a lot more, but essentially, if we put lots and lots of these together, there's a really cool example in here of an ambient drone pad. Again, I did not code this. Alex Chris coded this. But if we put a lot of this stuff together, we start to get like interesting music, you know? And so this is essentially all made up of the same elements. We've got a bunch of different oscillators and filters and things like that, but same basic building blocks. And this is essentially what's going on inside of an analog synthesizer instrument like the Weather Warlock that we heard earlier. Okay, now, if we want a little bit simpler of an interface to working with the WebAudio API, there's a really awesome library called Tone.js that just provides a little bit higher level convenient functions and things like that, and allows us to write a little bit more concise code. So for example, the LFO that we just coded up in the WebAudio API was like, we had to do a bunch of stuff. We had to create an oscillator, we had to give it a value, and then make a gain node, and then connect it to the gain node, and then connect it. In Tone, we get a handy dandy LFO method, where we can just tell it, okay, I don't need to think about multiplying things by a gain. I want you to go from this minimum value to this maximum value with this frequency. And likewise, we have a convenient filter method, where we can just say, I want a low-pass filter with this frequency and this resonance Q, and then we connect it all up. This is really just one layer on top of the WebAudio API. But this is what I have used to make a WIP project, a Waves in Progress project, that is essentially my little homage to Weather for the Blind. You can check it out at anjana.dev/here-there, which, yes, it does look like heart here, and that's deliberate. And I'm just going to show that to you real quick, or we're going to listen to it real quick. So what we've got here is some weather data piped into WebAudio and Tone.js, and by default, it's in Berlin, where I'm based right now. Let's listen to Berlin. It's apparently 14 degrees Celsius, wind speed something like 8 kilometers an hour. And if we tune to perhaps a more interesting destination for us, like Cluj, it sounds a little bit higher, because it's a little bit warmer. It's usually warmer everywhere than Berlin, no. But what about somewhere where it's almost definitely colder? Anchorage, Alaska. Much quieter. So, okay, this is just a little example. I won't play too much of it for you here, but essentially, what we've got now is we've got an instrument built out of the WebAudio API that we just saw that is now letting the data of the weather in a given place drive the values of all those little knobs and levers and the frequency cutoffs and the frequency of the LFOs and things like that. And so what I'm doing is I'm just grabbing some data from the free public keyless API, openmeteo.com, yay public APIs. And that gives me current weather conditions for anywhere on the globe. And what I've done is I've picked out a few choice attributes of the weather that I thought corresponded to like 4 different elements: earth, water, air, and fire. And so I've created 4 different voices, you could say, or 4 different of those like graphs between our sound input and our output. And what that essentially, it just has each of those voices is independent. It's hooked up to its own gain node, and then there's a merge that's happening, all of them together. So to zoom in to one of these, in the web interface, we can turn off the other voices and just listen to Earth, which is sort of the baseline here, which is based on the temperature. And so if we come back to kludge, eventually, hopefully, something happens, or it's broken. And so just to zoom in on this voice itself, what's going on here is I've got just the same things that we were talking about. I've got a triangle oscillator piped into a series of filters. In this case, I have a few. I have a high shelf filter that's just kind of cutting out, or sort of amplifying the higher values. This is just another shape of filter. Then there's a band pass, which is sort of like high pass combined with low pass. It only lets in the frequencies around the cutoff. And then there's a resonant low pass filter with an LFO hooked up to it, just like we just saw. The only difference is that the temperature values and the feels like temperature are being sort of piped in to the frequencies here. So Tone.js provides a really convenient little ramp to method that I can use to gradually change from one parameter to the next. And so essentially, I'm just playing with these, a lot of experimentation, to use these values to scale up or down the frequencies of both the oscillator that makes the sound and the LFO that changes how fast that filter sweep happens. So that's just one example. You can check out the code. You can judge it on GitHub. But let's zoom out and just, I want to hopefully give you a few takeaways to help you continue your audio adventures. Because like I said, tip of the iceberg, and I'm already 6 minutes over. Sorry. First of all, sound, visuals are cool. But sound can really make data resonate. I think it's really cool to be able to be like, I miss kludge. What does it sound like in kludge today? And go check it out and feel like I'm here with all of you wonderful people once I've had to go home to cold, cold Berlin. Okay. I also hope that we found that like synthesis is a little bit scary. There's a lot happening, but it's not so scary as I thought 6 months ago, because we can break it down into these 3 basic steps: make sound, shape sound, move sound. The possibilities with those basics and the few basic building blocks and a few other things that we didn't have time to explore today are truly infinite. You can go on and spend the rest of your life doing this stuff if you want to. But you don't need any special tools. You just need a web browser, because the WebAudio API can do it all. Tone.js can make it even more convenient in some cases. And I hope that this has provided you a little bit of inspiration to go forth and catch some waves of your own. So thank you so much for listening, and mulțumesc, and huge thank you to all my RC friends like Flavius and Joseph who helped me understand these things in the first place. And can I get a huge thank you for the entire JSHeroes family? Thank you all for being here. Yay!